In this problem, there is a robber and his task is to rob some houses in a locality, and there are houses in the locality in a row, and each house has some money in it. So maybe this house has $5 billion, this has $10 billion, this has $2 billion, $7 billion, and so on. The condition is that the robber cannot rob two consecutive houses. So if the robber decides to rob this house, then he cannot rob this house. So he has to leave at least one house. He can also leave multiple houses, but at least one should be left. Otherwise, people will call police. So that's the strategy that robber has to decide. And it's quite a popular problem, and it has been asked in many of these companies. So let's take an example. So let's say we have this number. So these numbers denote the money that is there in the houses, and these are in consecutive, the same order in which the houses are there. So let's say the robber robs this house number 2, house with a money of 2, then he cannot rob 7. So similarly, if he robs 7, he cannot rob 9 and 2. So how can we do this? So let's try to break this problem. So let's say we have 2, 7, 9, 3, 1. So what we will do, let's say we are solving for nth number, last number. So either the robber will pick this value or not. There are only two cases. So if you look at the last one, you can also look at the first one. We will look both the approaches. So let's say we are deciding for this value, and we have already calculated for everything. So first we are trying to come up with some recursive solution for this, so that we are breaking n in terms of smaller values of n. So either the last one is robbed or not robbed. There are two possibilities. So one case is that last one is not robbed, and the other case is that the last one is robbed. So let's say plus denotes it was robbed. So the robber picks 1 here. So he has to lose this one. He cannot rob 3 and 1 both. So in this case, what is the problem? The amount of money that he got from robbing this one is 1. So 1 is there plus what else? Whatever is the optimal solution in this part. Not till here, because this is definitely, we will ignore it. So n minus 2. So if this is n, then Fn breaks into two things. The nth house is robbed. So we get this, let's call it A. So An, it should be in fact n minus 1, but let's say it's starting from 1, whatever you are comfortable with. An plus Fn minus 2, where F is the optimal solution for this n houses, the best, the largest money that the robber can get. So this is one possibility when the robber tries to decides to rob the last house. The other possibility is that he sees that this is a very small value. Let me try with excluding this one and including this one. So in this case, the robber will rob n minus 1 and then Fn minus 3. These are the only two possibilities. Or Fn minus 1 is already solved, so it will be Fn minus 1. So these are the only possibilities. So let's get rid of this. So max of these two. So we had solved till this point. So if we don't pick it, it will be same as Fn minus 1, because we did not pick it. If we pick it, we will not pick n minus 1. So the best solution till this point. So, and we take max of these. So in terms of code, we can write Fn equal to max of Fn minus 1 and An minus 1 plus Fn minus 2. So here I am taking actual index n minus 1, or let's take n only. So it's very simple, but and this should work provided we have some base case, that is if there is just one element or just one house, then it will always rob that. If there are two houses, then max of these two. So these are the base cases. In fact, you don't need even this base case. Here you will add this number and max of 0, that is 0. If n is 0, then it's 0, nothing to rob. So the base cases should be n equal to 0, then 0, n equal to 1, then a of 0. Otherwise, this recursive formula. So this will work, but there is one problem. So let's see what is the problem. We have fn. We are trying to solve it, and we are expanding it as fn minus 1 and an plus fn minus 2. So let's ignore these things for now. These are constants. So for solving fn, we need fn minus 2 and fn minus 1. Again, when we expand fn minus 1, we will need fn minus 2 and fn minus 3. Similarly, here we will need fn minus 3, fn minus 4. So you will immediately see that we are seeing something similar to Fibonacci series. Here also we will need fn minus 3, fn minus 4, fn minus 4, fn minus 5, and so on. So here you see that fn minus 1, fn minus 2 is solved using this. If you expand this complete tree, and here we are also solving fn minus 3 and fn minus 4. But you see that these are solved here again. Fn minus 3 is already solved. Fn minus 4 is already solved. Similarly, fn minus 5 would also be there. These are all already solved. Fn minus 2 is also solved. So this entire thing is redundant. There are overlaps. So you see dynamic programming approach coming here. We have optimal substructure. That is, if this f optimally solves for fn minus 1 and fn minus 2, then we can optimally solve for fn. And also we have overlapping subproblems, overlapping solutions. So we will memorize these, store it. So there are multiple ways you can store everything in an array of same length as the house, or you just need the previous two values, like the Fibonacci case. So in Fibonacci, we keep track of previous two values because those are what we will need. So here what we will do, we will store the previous two values. So let's run through this example 27931. So let's do it bottom up. You can also do top down. So let's solve this problem. So we have fn. If n is 0, then return 0. If n is 1, return, let's say we have a. And I am writing n here, but we will need to calculate this n here, a dot size or length. If n is 1, return a0. So these are the base cases. Next, we will keep two values. What are these values? Let's call them val1 and val2. So initially this will be a0 and this will be max of a0 and a1. So at any point of time, val2 is the latest value, that is optimal solution till current. You can name it in a better way, previous and current. So val2 will be max of these two, and val1 will definitely be a0 initially, because if we have one element, this is the maximum. So this is val1, or let's call it v1, and v2 will be solution till here, current. So it will be max of these two. So v2 will be max of these two, that is 7. So this is 2, this is 7. Next, we will gradually increase. We will come here. In order to solve this, we need what? We need these two things. So this is the main formula. So you can easily convert from this recursion formula to dynamic programming formula. Whether you write top down or bottom up, it does not matter. Both are same. So the main task is how to find this recursive formula that we have seen. So either we take it or not take it. So if we take it, we get 9 plus v1. If we don't take it, then it will be v2. So what is the loop that we will create here? Till 1, we have already, it will return from the base case only. So if it goes beyond, that means it has at least two elements or two houses. So for I equal to 1, this is 0 and 1. So this is the second element, I equal to 1 to n minus 1. So what we will do, we will have val2 is the latest, so this will be max of val2 and ai current element plus val1. This 9 is nothing but ai, the current element. So this is val2, and then val1 will take the value of val2. We are shifting to the right, so val1 becomes this, that is solution till previous. So whatever was the solution till this point, now this is v1, and v2 is here, solution till here. But val2 is changed now, so better we will keep it in temp. And finally return v2, that's it. So let's write the code for this. If you want, I can write the recursion also, just to show you that will work for small test cases, but that should fail the time limit. So first let's write the recursive solution without DP, without dynamic programming. So if n equal to 0, return 0. If n equal to 1, or we don't need this one. Max of so we had taken max of n minus 1, this n minus 1 and n minus 2 plus current element. These are the two cases where once we include it or not. And so it will be rob nums n minus 2 plus nums n minus 1, and we are passing here till n. So let's see. So this works for this case. But you see, time limit exceeded, because you can see the recursion tree, how quickly it's expanding. We have 1, 2, 4, 8, 2 raised to the power n. So it's exponential solution. So clearly the time limit will exceed. Similar would be the case when you try to find Fibonacci using this kind of simple recursion. So let's get rid of this, but we will use this idea here, and we will use bottom up. Same base case. We had V1, so V2 is the current, till current. So that is previous and previous to previous. So I denote the current index. So max till here will be either max till previous value, that is V2, or we include the current, then max will till previous to previous, that is V1. So this is v2 and this is v1 plus nums I. So our answer is 1 more. Why? So we have solution till 0, 1. So we have to start from third element. Till 2 we already have this v2. So let's see if it fixes or not. It should. Now our answer matches. So let's try it on this example. Again an error here. It should be max of v1 or nums 0 and this, because v2 is the latest solution, latest best solution till previous value. Now the solution is accepted. And you can try a few times. It should be 0 millisecond also. So what is the time complexity here? We are doing just one pass of this array. So let me write it down. So time complexity is O of n. Space complexity is O of 1. If you don't use dynamic programming, time complexity would be 2 raised to the power n. Now let's complete this in Java and Python. Java solution is also accepted. And here also it's 0 millisecond. Finally we will do it in Python 3. And the Python solution is also accepted.